I'm very happy to be here. The first time I was in Kyiv was in 2016, I think in May. So I was here many, many times between 2016 and 2021. And I'm very happy to actually be back here. So, okay, so I want to start out. So I just kind of want to say a little bit about the goal of this. So, we have I should slow down with this. We have 6 lectures. And I want to start out very basic, and they will get progressively, a little harder and assume some more mathematics. The end goal is that I want to get to some point where there might be some ideas for research collaborations or other projects. So there's recently been a lot of these connections between descriptive set theory to number theory, dynamics, problems involving normal numbers. And I want to explain a lot of what this connection is. And I think that this type of connection can be used in other areas of math. So I think there can be this situation in mathematics where people work on this, people work on this. Two groups don't talk to each other so much, but there's a lot of interesting stuff in the middle. And so a lot of my approach of doing mathematics has been talking to this type of person, this type of person, this type of person, and cobbling together some sort of Frankenstein monster paper and publishing it. And so I think there are a lot of very interesting results kind of in between, and that's been very productive. So I'm going to be explaining kind of where I've been able to connect these results, and then maybe someone can have some other ideas, or there's going to be a lot of room to build up what I'm explaining. And just to get an idea, there's undergraduates in the audience? Any high school students? I've given versions of this talk to enthusiastic high school students, so it's possible. So I'll aim this for, fairly simple. I'm not going to assume very much. So let's start off with just what is the idea of a normal number. So let's start off with some simple things. So every real number has at least one decimal expansion. So 1/3 is 0.3333. And so on. 1/4 is 0.25000. I'm writing this as having infinitely many zeros. And we can also say that's 0.24999 and so on. So sometimes this expansion is not unique. That causes us no problems. So whenever I talk about the decimal expansion, I'm referring to this one. But it won't change anything for this talk if you use this one instead. Some things are more interesting. 3.14159265358 and so on. This is Odin Chotiri Odin Piat Devyats? What?
Russian and Ukrainian style.
Yeah. I know some things I know in like Ukrainian and some in Russian, so the numbers I learned in Ukrainian. And so when I travel some places, I say it in Ukrainian or Polish, and people usually figure it out. So, okay, good. So we got Ukrainian numbers. So you can have some more interesting things happening sometimes. And there can be this question is, when is this random? And I'm going to put random in quotes because there are many ways of interpreting this question. We're only going to look at one interpretation today. And I want to remark that really very little is known about this sequence here. So let me actually write the first open question. Question. Does the digit, say 7, occur infinitely often in the decimal expansion of pi? This is very, very, very out of reach. No one has any idea how one would even begin to tackle this problem. We're going to ask a more interesting question even a little bit later about pi, but just something this simple. It could be the case that the decimal expansion of pi has only 3s and 5s after some point. We just kind of assume it keeps looking like this, but nobody has any actual proof. You know, there are people who have been writing computer programs to compute, I don't know what the current record is, maybe a couple trillions. Someone sent me a Linus Tech Tips video about like them computing some new record, and I haven't watched it yet, so maybe there's a new record on this. People know a lot of digits, but you know that doesn't tell you about what happens long term. So I want to actually even like ask if this is going to be random in some sense, but what do I mean by random? We have to be very careful about this. And that marker wasn't quite doing too well. Let's try this one. So, basic idea. So if we have digits, 0, 1, 2, up to 9. Okay? If this is random, then each of these should show up with probability, also in quotes, because I'm going to write it precisely, 1 in 10. Right? Imagine you're rolling some 10-sided die. You would expect each of these to show up 1 in 10 times. Okay. Furthermore, you would expect 0, 0, 0, 1, 0, 2, up to 9, 9 to show up 1 in 100 times, 1 in 10 squared. Everyone agree? That's assuming that these are fair dice, so there's no dependency on the previous roll. 0, 0, 0, up to 9, 9, 9. You should expect to see each of these 1 in 1,000 times. Okay. And so on and so on and so on. And we would call such a number normal in base 10. Now, I haven't defined what I meant by probability here, so we need to be careful with that. So does the basic idea and motivation make sense? We'll talk in the next lecture, there's a very, very deep connection with dynamics and ergodic theory and other things. So there are reasons we care about this concept of normality and the decimal expansion being random. So let's actually just define this technically. So what we're meaning by probability is that, let's say you have like the digit 5 or something like that. So what we want to do is we want to say, go out to n positions and count how many 5s you see, divide it by n, and then take the limit as n goes to infinity. And that's the notion of probability that we're using. We're not using anything with like measure space or whatever, so it's just going to be this. So nothing with measure theory. So we let b greater than or equal to 2 be an integer. I'm just going to define this in base b. And b be a member of 0, 1, b minus 1 to the k. So this is a block of digits. I'll say what I mean by this. So in other words, like this is a block of digits here, like 999. That's 9 followed by 9 followed by 9. So these are the allowed symbols in base b. And we take a k tuple. And we define n sub n b of b comma x to be the number of times the block of digits b b occurs in the b area expansion of x.
It's better to change the time.
Yeah, I was just thinking that. So this is the second one already. Let's try this third one and see what happens. Is this readable at all, what I wrote so far? Okay, so we'll continue with this other one. I'll try this one too. This is a new one. I just got this one. I'll have this one ready.
There are some on the table. They are better.
I'll try this one next if this one starts going out. Is the B area expansion of x up as the number of times this occurs in up to starting position. N. Okay, so just to give an example, so we would have, let's use pi. Let's use pi minus 3 just for simplicity. So let's say the number of occurrences in base 10 up to position 2 of 1 in pi minus 3. Okay, that's position 1. Position 2, I see exactly at 1, 1. This is 1, but the number of occurrences up to position, let's say 7, of 1 in pi minus 3 is going to be 2. Right, I see 2, and I'll write just one more example. The number of occurrences up to position, let's say 9 in base 10 of 5, 9 in pi minus 3 is 1. Because we see this 5, 9 right here. Overlaps are okay. So for example, if we had something like 5, 5, 5, 5, 5, 5, we're looking for 5, 5, 5. This is an occurrence. This is also an occurrence. This is this, and so on. So it's okay if they overlap. That causes some problems for some things, but that's the definition we're taking. And so definition is that a real number, x, is normal in base b. Okay, we will switch markers now. Normal in base b if for all k in n, and just a remark, because we're talking about logic and set theory as well as number theory, right now n starts at 1, so it's like counting floors in Ukraine. So sometimes, set theorists count like floors in Poland where they start at 0 instead. So we'll have to be a little careful because there's different types of mathematicians touching this stuff, and the computer scientists are also starting at 0. But in this case, we mean starting at 1, and then for all b in 0, 1 up to b minus 1 to the k, the limit as n goes to infinity of n sub n b of b comma x over n is b to the minus k. So the probability of every block of length k is 1 in b to the k. Particular in base 10, if you have a block of length 7, it'll occur with frequency or probability 1 in 10 to the 7, 1 in 10 million. Okay, so does the definition make sense to everybody? Okay. So what about examples of normal numbers? Say, let's just start simple. Does anyone have, who doesn't, like not Roman or Professor Torbin, like someone who's not one of you guys, do you have an idea for what could be an example of a number that's normal in base 10?
I think it is the first number, like 0.1234 and forever with just a natural sequence.
Yeah, you kind of do the dumbest thing possible and it works.
Yes.
And so this is the Champernowne number. Champernowne in 1933. And this, of course, continues, then you go up to 999 and so on. So has anyone proven that this number is normal? So that's an exercise, and it's a kind of a hard exercise. Prove this is normal. So you can tell me tomorrow what you come up with. Of course, I can't give you a grade, so this is optional, but it's recommended to get an intuition. So this is something that's a fun problem to give if you have one of these students who's smart, enthusiastic, has a lot of energy, needs something to do, and you need something that they can make like some progress on, but still kind of has some trouble finishing. This is a great problem because it's harder than it looks. You don't need to know almost anything to do this problem, but all you need to do is you need to estimate this limit. And the problem comes that, like, okay, you're given an arbitrary n and an arbitrary block b, and what happens if that n puts you in the middle of a 1 million digit long integer? The estimating and counting can be a little bit more complicated than you might think. The common mistake that people make when you give them this problem is they only look at the limit along a subsequence. Like they stop here and count, then they stop here and count, and so on. And I want to emphasize that doesn't actually tell you anything because you're only checking what happens to this along a subsequence, not along the integers. So that's what makes it harder. Any other ideas?
Is it 10 normal, like in base 10?
10, okay, good question.
Or is in any base?
Base 10.
In base
So,
10.
yeah, let's just start in base 10. Okay, here's the number 10, 10.000. Okay. So this is not normal because, let's look at
the
sorry,
question
this was
was-
not my question.
Oh, sorry.
My question was whether this exercise number is normal in base 10.
In base 10.
Yeah, oh, this is normal, okay, this,
In base 10.
base 10, yes.
Because we are writing digits in base 10,
Yes.
right? And if we do them in base B, will this be normal in base B?
Okay, there's actually two questions here. So this, let's call this a real number, let's say C sub 10, to mean Champernowne number in base 10. Okay. We could also write C sub B to mean Champernowne number in base B. And we note that these numbers are different, right? Because in base 2, for example, C sub 2, if you go in binary, this is 0.1, 1, 0, 1, 1, 1, 0, 0, and so on. Since this first digit, this first binary digit is a 2, we know that C2 is going to be strictly greater than 1/2. And this number here, written in decimal, we know that since this first digit is a 1, this means that C10 is strictly less than 2/10. So these numbers are not equal, so C10 is not equal to C2. So I first want to make this remark. Okay. Now the claim is going to be that CB is normal in base B. This is no more difficult to prove than proving this is normal in base 10. Identical proof.
I'm sure that C10 is not normal in base 25.
We're getting to that. And as far as I know, nobody knows. So, is C sub P normal in base Q? And in some cases, yes. For example, C sub 10 is normal in base C sub 100. There's a theorem that will guarantee that. But as Professor Torben just asked, is C sub 10 normal in base 25? And I believe this is an open question as far as I know. I don't think anyone has established this either way. These types of questions where we switch between bases can be very difficult. And so this is where I kind of saw Masha's question as being two different questions. You know, if you just change the base, are you still normal in that base? But if you fix the real number, are you normal in a different base? Probably. But we can also put this as a question to try to do. It's not going to be as hard as the one with pi about the digit 3 showing up, but I think this would still be pretty difficult. Any other questions on this before I move on? We can go as slowly as we want. There's a lot of good questions here. What about other examples of normal numbers? Any ideas? Say normal in base 10.
What do you mean at all by, like, if you write it in base 10 and then ask if it's normal in a different base? For example, it's an irrational number.
Sure.
Do you have to approximate it by rationals and
So C10 is a real number. So, you know, real numbers don't depend on there being any numeration systems, right? You know, this is, you look at the completion of the rationals with respect to the Euclidean metric, whatever, you get a real number. And you can say, is this real number normal in any sense? There can be, we'll talk about other senses with continued fractions and other stuff later. And so there's an algorithm to generate an expansion in some numeration system. So I can even just kind of say what that algorithm is now, because it will be important. We'll do it over here. Let's just do the binary one. So like let's say you have a, you know, x is in, let's just say in 0, 1. Okay. How do we generate, and I hate to say like the binary expansion. So we, you know, there's 2, but we're going to pick a particular one.
Sorry, but the Champernowne number is not the simplest example of normal number.
You said it is or isn't?
It seems to exist essentially easiest example.
Yeah, so that's an interpretation. you know, that it's the one to our psychology that's the easiest. There's many other things that can pop up.
So just produce all possible pairs and triples and so on in uniform distribution from stage to stage. So 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. After that, 3 triples and so on.
So I think, yeah, you mean instead doing something like 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, this variation.
Yes, and then triples and...
Yeah, this also works. And then 1, 0, 0, 0, up to 1, 1, 1, 1. This also works if you concatenate these. Yeah. There are several variations of the Champernowne number. So it's actually a little bit more difficult, as I remember, to do the estimates on the Champernowne number than on this, but it's a similar idea. Yeah, so there's a couple other things. I'll just answer this one here with generating a decimal expansion, and then I want to get back to some others, because there are some other nice, simple examples. If you want to generate, say, a binary expansion, we define the map T2x is 2x mod 1. And when I say mod 1, that means give the fractional part. This is the notation that's usually used. So this is a fractional part. And so just think back to grade school. What does it mean? Okay, let's say in base 10 to multiply by 10. You move the decimal point one direction, and you divide by 10, you move it the other direction. In binary, multiplying by 2 moves the decimal point or the binary point. And so let's graph this map, and it's going to look like this: 1/2, 0, 1, and then it starts here, and then it goes here. And we're going to call this interval here, we're going to give it a label 0, we're going to give this one a label 1, and we're going to define 0.A1, A2, and so on as follows. We say that A1 of x is equal to 0 or 1. Here x is in 0 to 1/2, and here x is in 1/2 to 1. And then A sub n of x is t is a sub 1 of t to the n minus 1 of x. So actually I just talked about this. I'm teaching an algorithms class in Poznan right now, and we were going over, you know, I'm a little biased in this, so we're talking about some algorithms from enumeration systems. And if you do this, if you take a real number and you perform this algorithm, then this generates a binary expansion. So to get to this question about what does it mean for, say, the Champernowne number in base 10 to be normal in base 2, it means, okay, this is a real number right here, and apply this algorithm here to that real number, and then you get a binary expansion. It's going to look crazy. I have no idea what's going to happen. It's probably going to look like a normal number, but there's not going to be any clear pattern. So when you do base conversions, things usually just get kind of crazy. So does this answer your question? Let's continue. Oh yeah, fun question as well, I might as well write. So, is pi normal? In base 10, for example. Doesn't matter, we can take any variation of this question you want. So I think some years ago I remember on Facebook seeing people post things that, like, you know, every book can be found in the decimal expansion of pi or other some such nonsense. And this is assuming a weaker condition than normality, but that basically every string can be found in the decimal expansion of pi, and we don't know that. Harder question, is pi normal? So there's a good number theorist in Graz, Austria, Christoph Einsleitner, who's dealt with like a lot of this type of stuff. And at this conference in Poznan a few years ago, he called determining the normality of pi a problem for the next millennium. So along these other things where we just don't have anything connecting. You know, there's just like with the Riemann hypothesis and some other things. It's not as important as that, of course, but there just isn't that connection. So like the tools to solve this problem just don't seem to exist. As simple of a question as it seems to be. So it probably is. I mean, there's kind of a philosophy that a number is probably going to be normal unless there's an obvious reason that it isn't. That's kind of the feeling. I mean, I tend to go by that, but of course we need a proof, and we don't have anything like that.
There is nothing special about base 10 then, and then we should, if it's normal, we should expect it to be B normal for any B, right?
Probably. So there is an algorithm, there are some special things, I think, about the hexadecimal digits of pi. So in, I think, 1997, Simon Plouffe, I believe, came up with an algorithm to compute an isolated hexadecimal digit of pi. So there's some information this gives you, not that much, but it could be the case that there may be some like very special property of pi related to some series expansion where you may get information about another base before base 10, but it's not really clear if that's the case or not. It should be normal in all bases. I would be very, very shocked if it's normal in base 10 but not base 7. I'll write down another one that's, let's say not an exercise, but is also almost an elementary problem. This is due to Copeland and Erdős. And this is in 1946. Points 2, 3, 5, 7, 11, 13, 17, 19, and so on. So this number is normal in base 10. And you know, it's the same thing in any base. Doesn't really matter, like with the Champernowne number. So I think this is more interesting, right? And it's mostly a counting argument. There's only one non-elementary thing that was used, the prime number theorem. So this is this fact, like limit as m goes to infinity of pi of x over log x is equal to 1. This is the number of primes. This is equal to x. So this is considered the only non-elementary component of the proof. You basically do a big counting argument, and it turns out if there are enough primes, I can write the condition after this if anyone's interested, then the concatenation will give you a normal number. And according to this, the set of prime numbers is almost positive density. It's like really, really, really close. So the only reason, so there's nothing like particularly special about the prime numbers as to why this gives you a normal number. It's just really that there are enough of them. So anytime you have enough of a certain class of numbers, then the concatenation gives you a normal number. And it also works for square-free numbers by their theorem. So you take square-free numbers. So a number is square-free if it isn't divisible by any squares, right? So like 12 is not square-free because it's divisible by 4. But let's say 14 is square-free. So 0.123, well, 4 is not square-free, 5, 6, 7, not 8, not 9, 10, 11, not 12, 15, so on. This also gives you a normal number. Here's a fun one. What about 0.248, 16, 32, 64, 128, and so on. What do you think about this one?
There is no 5.
What?
There is no 5.
There will be eventually.
Okay, yeah, 6.
Yeah, 65,506. Yeah.
Yeah.
But the density of even digits is bigger than the density of odd digits.
Is it? It's a good question. So I forget, there was even an Erdős question about what happens. I think, as I recall, there was still a problem with Erdős where he asked, like, is there some capital N where any n bigger than capital N guarantees that 2 to the n has every single digit in it? So I have to double check that, but that's a very basic question about powers of 2. It's an old Erdős question, still open. And figuring that out is still nowhere near showing that that is normal. So this is already something much harder than a very difficult Erdős question. Of course, this construction does not give you a normal number in base 2, right? Because if you do this in base 2, it's going to look like 0.1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 3, 4, and so on. Clearly, that's not normal in base 2 because 0 has frequency 1 and, sorry, 0 has frequency 1 and 1 has frequency 0. So that doesn't work. Any questions so far? So I want to also mention the idea, because this will come up as well later, of a computable real number. And let me see, I think I need another marker because this one's running out. And I want to be a little informal about this. I don't want to talk about primitive recursive functions and Turing machines and whatever. We're just going to be a little informal. Does everybody have like a very vague basic idea what a computer program is at least? Like a line of code, if it's in Python or C or whatever, just some vague idea. That's all we need. So computable. So we say that informally, X in R is computable if there exists a computer program, let's say, that can approximate X to arbitrary precision. So you may think, okay, you have a real number, you can just give more digits of its decimal expansion, you can give more binary digits, whatever, but that's not always the case. So I'll give an example of a computable number. Let's take pi as an example.
Any algebraic number.
Any algebraic number works as well, correct? Yeah. Yeah, you can, I'll take pi. It's a really simple one because the algorithm here is going to be really, really basic. So I think for algebraic numbers, let's see, if it's a real number, you can use Newton's method. There's probably some algorithm for complex algebraic numbers that have to think. How do you approximate, like, say you have a polynomial with only complex roots and it's something like complicated. I know there's a way to do it, but I can't think how to do it off the top of my head.
Like any approximation algorithm, how to determine root of continuous function.
But complex roots. So I guess if you could just use
real number.
Yeah. So okay. So you mean a real algebraic number? Okay. Yeah. So yeah, you can use Newton's method for that, I believe. But for a complex one, I'm not sure. I know there's a way to do it, but I don't know the algorithm. Because it could get complicated, right? If you have some like 100th degree polynomial and it has like, only complex roots, how do you, there's some sort of matrix methods, I think, but I don't. We'll stick with this because it's easy. Pi is 4 inverse tangent 1, right? So it's, and inverse tangent, right? This is going to be 4 times 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7. I'm not giving a good way to compute pi, just a proof of concept. This is a terrible way to do it. But let's say that, okay, you want to use this very, very slow method to give you digits of pi. Well, all you need to do is you do these divisions. How do you do a division? Well, you can, like 1 over 7, right? This goes in once, 7, 3, and then this goes in 4 times, you get a 28, bring the 2 down, and so on, right? So doing divisions, clearly you can tell a computer program to do that, and how many steps to take it out. Anything I can do by hand that's following an algorithm a computer program can also do. Those who care can formalize what I just said. I'm dancing around some things. You have subtraction and you have addition, and then you have multiplication. So basically, if you can hypothetically approximate pi as closely as you want, just using these grade school algorithms as far as you want to take them out. So pi is computable. But there's a problem because there are countably many computer programs, right? Because a computer program is finite. So there are going to be countably many computable real numbers. But there's uncountably many real numbers. So, you know, it's most real numbers are not computable. So actually giving specific examples, like I can give some specific examples later if anyone's interested. But if we want to count a number as being an example of a normal number, we require that it be computable. So there were some early examples, for example, due to Sierpinski or due to Lebesgue, of, say, numbers that were normal in every base, that were, let's say, non-constructive. They were not computable numbers. They used some level of axiom of choice or whatever to extract some information that you wouldn't be able to ever write down. So we're putting this as a requirement when I ask for examples. So the first person to come up with a number that's normal in every base was Turing. And it was 1939 or 8, I forget, it was an unpublished manuscript. So Turing had some algorithms, so he gave a number normal in all integer bases. In all bases, b greater than or equal to 2. Now, all these are algorithms, right? This is an algorithm too. It's aesthetically pleasing because it's prime numbers, but well, how do you compute the prime numbers? Okay, there's like the sieve of Aristophanes, or you can just write some sort of while loop or whatever. Either way, generating prime numbers is some sort of algorithm. I have these memorized, so I don't need an algorithm. I can just, you know, pull them out of my brain. But after some point, you don't know those. So there's always an algorithm, even if you're writing something like this. If it's a Champernowne number, it's a very simple algorithm. Add 1 at each step. Generate the next prime number is more complicated. And this is something I don't even want to give any indication here, but he had something really bad. And to get n binary digits, this needs big O of steps. Any guesses as to how many computations, just to get n binary digits, his algorithm? It's something horrible. N squared, that's bad for sorting, right? Bubble sort is n squared.
Exponential.
So you mean like 2 to the n or something? Or?
E to the n.
It's worse than that even. What is it? Factorial? And that's even worse than factorial. 2 to the 2 to the n. So I think that's one of those things, like, you know, if n is, maybe it was 7, that's already like kind of the most you can get. Then the next one, it would be like heat death of the universe type of situation. So this has been improved significantly by Becher, Heiber, Slayman, I think. At least Becher and Slayman. And maybe others, I forget. Maybe Heiber. This was in 2013, and they have polynomial time algorithms. And you can even get it to big O of n to the 2 plus epsilon. So in other words, for all epsilon greater than x0, there exists an algorithm that's big O of n to the 2 plus epsilon that generates n binary digits of a number that's normal in all bases. But the smaller you get epsilon, there's some sort of loss of efficiency. For those who know this buzzword, you have worse discrepancy. So somehow or another, the limit converges slower, but you still get some normal number. Probably pi works as well, but you know, that's out of reach. So I wanted to make a few other remarks. Does the term measure or measure 0 make sense to everybody? And if not, that's okay. I want to make sure we have a background here because I want to make this lecture simple. So does everybody, and then please don't feel like bad about raising your hands and saying no. Does the word measure 0 mean something to everybody here? Undergrads as well? To you guys, do you know it? It's okay if not.
Almost sure.
Almost surely. Okay, they know almost surely. Okay. So if you know the term almost surely, you guys know this? Almost surely?
No.
No. Okay, thank you.
Skeptically confident.
Okay, thank you, I appreciate that. It's really difficult, but and I'm guilty of this, but like not asking questions in math is kind of dangerous, so I want to slow down. It's going to speed up later, but for here I want to be slow. Okay, so let's define this because this will be, this is a useful concept for those who haven't seen it or want to review. This is going to be a notion of, say, largeness or smallness. And so we say that a set, let's say I, equals, let's say, in. Let's not say n because this could be uncountable. Let's say j, where j is in some set j, is a epsilon cover of S subset of R if the sum of the lengths of the intervals is less than or equal to epsilon and the union of I sub j, where j is in j, contains S. So let me just be kind of, that's an abstract definition. So basically, let's say that we have I is equal to, let's say, minus 1 to 1 and 0 to 2. Okay? And let's say S is equal to, let's say, 0, 1/2. Okay? So we note that, so I is a 2 cover of S. Right? No, sorry, not 2, 4. 4. Sorry. Right? Because that has length 2 and that has length 2. And when you union these, right, the union is just minus 1 to 1, union 0 to 2 is minus 1 to 2. So that contains this right here.
Some misunderstanding can occur because usually epsilon cover means that any offsets the diameter less than epsilon, not the sum.
For this, okay, so for today, we're going to say the sum is less for this purpose. Is there a language you prefer other than epsilon cover, maybe?
The element of this covering diameter less than epsilon.
For this purpose, we need the sum. We'll stick with this for now, but it could be defined differently, and we say that S subset of R is measure 0. Measure 0 if for all epsilon greater than 0 there exists an epsilon cover with my definition of epsilon cover there of S. Okay. So for example, S is just a singleton pi. This is measure 0 because you could just say something like I is equal to just the interval pi minus epsilon over 2 to pi plus epsilon over 2. Okay. So that works. Much more interesting is a set of rational numbers. So this is counterintuitive, like when you see this the first time, this is also a set of measure 0, but it's weird because this is dense in the set of reals. Let me just very quickly prove this. So this is a countable set, so we can write this as Q1, Q2, Q3, and so on. And we let I sub n be, let's say, Qn minus, I guess this is going to be epsilon over 2 to the n. We may have to adjust that exponent. It's either n or n plus 1. Qn plus epsilon over 2 to the n. So we consider all these intervals in, and so clearly, if you union this, it contains the rationals, right? You look at a rational number Qn, it's in this interval. So union of in, so Q is contained in union of in, but sum of the length of in, right? This is going to be sum of epsilon over 2 to the n from 1 to infinity. And that's just equal to epsilon. Right, that's a geometric series. So the set of rationals is zero measure. If you haven't seen that before, something to think about tonight. Yeah, it really threw me off when I first saw that. Like, you can see the proof is correct, but like, how is that possible that that's true? But it is. Okay, so I'm going to make a claim about the set of normal numbers. And I didn't mention who first came up with the normal numbers, so I'm going to say this along with the claim. So for starters, a set S subset of R is of full measure if S complement is measure 0. To change markers, let's go to, maybe the blue one was working. Yeah, I think blue was working. Okay. So this is corresponding to this complement, or this concept of almost surely. So some of you have had probability, right? So we say that, so Borel, 1909, defined normality and proved that the set of numbers normal in all bases, normal in all bases, is full measure. M-E-A-S-U-R-E. Okay. So you can think if you're picking a real number uniformly at random, then with probability 1 or almost surely, then this number will be normal in every single base. But a lot of numbers we think of are not normal, like 1/3. This is not normal in any base because its base B expansion will be eventually periodic. So no rational numbers work. We saw some examples of numbers that do. There can be numbers, I didn't write how to do this, but there can be numbers normal in some bases and not others, and there's a lot of crazy stuff that can happen. But for the typical number, it's going to be normal in this sense. And so Borel, he used, does this term familiar, SLLN, strong law of large numbers? So have you guys seen this in probability? I'm not going to have time to go over those theorems, but let's just say there's a nice theorem from probability theory that can be used here. But the problem is that Borel gave a little bit of a different definition of normal number. And there's a little bit, a lot of these theorems from probability theory, you need independent random variables. So you can look at something like a block B occurring, and you say it's at this occurrence, and then checking at another place is another random variable. But the problem is that we have these overlaps that can happen in our definition of normality. So this is not really the way that this is handled right now with the definition that I gave. So Borel gave a different definition that took quite a bit of work, at least back then, to show was equivalent to our current definition. So I'm not going to go into too much detail on that unless someone wants me to do so. So in this particular sense, though, like nowadays, it's better to look at this if you know what this means. Birkhoff-Ergodic theorem is a good way. There's some other ways from uniform distribution theory. If you don't know what that is, don't worry. We'll talk about it in later lectures. So normal numbers are large in this sense. Does everybody know what a meager set is in the sense of topology? If not, that's okay.
I know literally topology.
Better to define.
Okay. Right. Let me see where we are on time. I don't have too much time. Let's just say we have about 10 minutes left. I want to get to a couple other things. Let's say in another notion, maybe I can define this in the next class in other ways. Normality is rare. So in a topological sense, set of numbers normal in base B is meager. Maybe I will define this tomorrow, but let's just say that it's not that important and we're not going to come back to this so much later. So there's another notion where the set of normal numbers is small and does not agree with this notion from probability theory. Set of numbers not normal in base B has, and I'm going to put down a word, I'll ask you guys if you know what it means in a minute, full Hausdorff dimension. So maybe you guys know that just because of some people in the room that work a lot with fractals. Do you guys know anything about fractals or Hausdorff dimension? Or let's say, does everybody here know about fractals or Hausdorff dimension? If not, that's okay. So have you guys seen it?
I'm now fractal.
Okay. Let's say that maybe we can define this in a future lecture. There's another sort of sense that you can look at the set of non-normal numbers as being something called a superfractal that's big. And in fact, it's not just this. The set of numbers, in fact, also the set of numbers normal and no base has this property. Okay. So often in math, we care about when there are a lot of some object. And I want to remark, this is also something that's like probably a different mindset than, let's say, coming from high school one may have, is if I were to say, show that there are normal numbers, probably the first thing that, say, a high school student would do would be to try to come up with one, right? Because that's a way to do it. You actually show the object. But sometimes it's not even possible, for example, to give computable examples. In base B it is, but in other numeration systems we can look at, it's actually not always possible. And so sometimes you might have some theorem, there's, say, in this case, a theorem from probability theory, where you can show that there are normal numbers by showing that there are a lot of them. So that happens sometimes. It's kind of weird. That was, to me, a little bit unsettling because I like having concrete examples. I like saying, okay, here's a Champernowne number. That's a normal number. Here's something else. But there are situations, like I said, maybe we can talk about it later, where you can come up with numeration systems where there are literally no computable normal numbers. There are some papers on this. That can be done. And I wanted to also put a little nod to some people in this room as well. So we talked about this definition of normality, right? We have this limit that defines being normal. And how can a number fail to be normal? One way is that the limit may not exist. Sorry, well, let me get to that in a second. One way is that the limit may not be what you want it to be. Like, for example, maybe you're in base 10 and it turns out that the digit 5 shows up 73% of the time. Well, in that case, the number is not normal. But just saying, negation of limit equals something you want, that doesn't mean that the limit exists, right? That's a case as well. So there's also something called, and I'm not going to be planning to talk about this, but there's also something called essentially non-normal numbers. And these are cases, these are numbers where none of the digits actually have a frequency, where the limits don't exist. And this is also something very interesting. So it's not just that the set of normal numbers themselves are interesting, but these are one very interesting subset of the non-normal numbers. And there are many other interesting subsets of non-normal numbers that do crazy things. I wanted to make another remark as well, and we can maybe even prove one of these possibly tomorrow. Suppose that X is normal in base B. and Q is a rational number, then X plus Q is normal in base B. And also X times Q is normal in base B if Q is not equal to 0. So normality is preserved by rational addition and rational multiplication. And there was actually a question until recently, what about the set of numbers that preserve normality under multiplication? Like, are there any other numbers that will always do this? And I mean, I talked to actually some very clever people about this question, and there was no answer until I went to Oulu in Finland. So this was kind of a funny trip. So Oulu, it's like right on the Arctic Circle almost. It's like 65 degrees north. So Oulu. So this is in Finland. So I spent a week and a half there. There was someone I was going to work with, and I gave a talk. And I mentioned this, this kind of question about normal numbers. And I got an unexpected answer from someone in the audience. It turns out that there is another paper. Barak Weiss was one of the authors, and it was entirely a fractal paper. But one of the interesting corollaries of this paper that I didn't even know existed because it was really entirely out of my interest or whatever I would look at, is that there are no other numbers other than rational numbers that preserve normality under multiplication. That's kind of funny.
The reference for this result.
I can email you.
It's not clear for me.
Yeah, I can email it to you. In terms of why that's true, I don't understand this paper. If you want to understand it and explain it, or if you're just, I'd be happy to hear. But why is that the case? I have no idea. Just that it is the case. So
The rationality is very
yeah. So it follows just
general
rational
assumption.
Yeah. So are there any irrational numbers that will always preserve normality by multiplication in base B? No, as a corollary of this paper. Rational numbers do it. I think this was an exercise in Kuiper's and Niederreiter's section 1.8. So both addition and multiplication, I think, were exercises. I think it was exercise 10 maybe. So we can maybe do one of those tomorrow, depending how far we get. What about the set of numbers that preserve normality under addition? So what about the set of, let's say, y, such that for all x normal, x plus y is normal. So there are a lot of interesting things here. So this is actually kind of a funny result because this just even has to do with kind of how math works with communication of results and everything. So there were several people that were giving examples of numbers with this property. And this set, for those who know what this means, it's not clear that this is even a Borel set. So you're doing an uncountable quantification. And so there are, I don't want to say like a lot of papers, but there were maybe 3 or 4 papers giving some examples of numbers that have this property that are not rational. But it turned out that there was a paper in 1976 due to Rosie in Acta Arithmetica that fully classified these numbers, so there was no point in people writing those papers because it was already fully classified. And what's even funny is, so Jan Bajot, who wrote this big book on normal numbers and has like a ridiculous number of references, Jan Bajot is a very good mathematician, great guy, and he didn't know about it even though he wrote about it in the book. So somehow or another, until 2016, basically, this result was kind of forgotten, and...
It's empty set.
This?
Yes.
No, it's big.
Well,
It says Hausdorff dimension 0, but...
Actually, for any x, you can choose minus x instead of y.
No, this is the set of all real numbers, y, such that for every single normal number in base B, x plus y is normal. So an example...
Positive.
So
X
the
and
rational-
y.
So for example, it contains the rationals, but my claim is it contains many more things. So basically anything with zero entropy is, informal. I can say more, but it's a Hausdorff dimension 0 set, but there's a lot of things in it. And Rosie has a full characterization. I could say what the characterization is later, but there's a lot of things. And so I think, probably, I think this number, right, this sum of 1 over 10 to the n factorial, this is an example of such a number that preserves normality in base 10 under addition. And that's irrational, it's transcendental.
Actually, in any case, X and Y should be positive. Instead, if you choose
I don't think it really
X
matters.
minus Y, you obtain 0.
Oh, right, yeah, yeah, oh, I see what you're saying, yeah, yeah, sure, we can say maybe in 0, 1, okay, sure.
Okay.
Yeah, we can do that, okay, I see what you're saying. Okay. So, but anyways, this is one example, and okay, so it's not, yeah, I understand. Let me see how we are on time. So we're slightly over, so let's say that I'll call it a day for here, and I want to talk about like the connection with uniform distribution tomorrow, so this will still be a fairly basic lecture, and I think maybe the following one after that, no, I think the next one's Cantor series. Maybe the first few won't be too bad, but then it'll start to get a bit harder when we start talking more about dynamics and descriptive set theory. Okay, so I'd say that's it for now.
Any questions, please?
Why do we say that normality is rare if we said that it is full measure?
Well, it depends on the notion of rareness. So if you say from it's a meager set, it's a countable union of nowhere dense sets. So from that perspective, it's rare. From the set of probability theory or measure theory, it's not rare. So these are good examples of where these notions disagree. So when we talk about notions of largeness in math, and there's another one as well. So if you've ever heard of Schmidt's game, I wanted to talk about that, but the time was running out. So being winning in the sense of Schmidt's game is a stronger property than having full Hausdorff dimension, and it's a interesting current thing that people are studying. And the set of non-normal numbers is large with respect to this game, and the set of normal numbers is small. So it depends on, so basically like, it seems to be that the pattern is any notion of largeness you pick that's like not measure theory, you get rareness for normal numbers, but then normal numbers are big in terms of probability or measure theory.
Thank you.
And this two rule working for exist Q from rational sets or for all Q?
For all Q's. So basically any time you add a rational number to a number that's normal in base B, you get a number that's normal in base B.
Okay.
Thank you for very interesting lecture. My question is about some methodological or pedagogical nature. Do you know some textbook where different methods for proving of normality are collected?
Yeah, so this is this Jan Bejode book, which, by the way, is actually great because if you Google it, you get like the PDF like right away. So Veronica Betcher has it on her website, at least last I checked, so you can even just download it. Let me find the exact name of it because the author is Jan Bejode, and it's let's say it's not aimed at undergrads, but let's say this is Jan Bejode. And let me check this title. So this is showed. Let's see his title.
Complicated to understand all letters.
Yeah. Okay. The title is Distribution Modulo 1. And Diophantine approximation. And so as I recall, like normality starts in chapter 4. Starts chapter 4. So there's an introduction on uniform distribution and a few other things in the first 3 chapters. Then I think chapter 4 through 9, I believe, are on normal numbers. This is, I think, was this 2012? This was published, something like this. Let's say this is like around 2012. And the reason I'm mentioning the year is it's already obsolete. Like it was because so much stuff has been done, in fact, was inspired by this book as well. So there's some interesting open problems that people didn't know about that Jan Bejode put here and then people solved. So I'm sure at some point, new edition of this book would be useful, but this is the best thing at this point now that has, let's say, results that are present as of 2012. And it focuses more on base B. So I think continued fraction normal numbers and other things like this aren't dealt with until like one chapter, which is like chapter 9.
Questions? Any questions? Okay, so finish for today. We'll wait you tomorrow for the next interesting stuff.
Thank you.
Thank you, Paolo.